Good evening. Today's lecture is based on the meshing, the computational fluid dynamics. So we've spoken about meshes and discretization often during the last few weeks, and we've realized the importance of the discretization, that is, dividing the domain into small pieces. So now there are various ways to go about with it. So there are two broad categories. One is called the structured method. The structured category, and the other is unstructured. So basically, what happens with the structured grid is that there are certain rules and methodologies which have to be followed in order to fill the domain with the structured mesh. So this is creating a structured mesh is generally a more rigorous process. It involves the engineer or the user more as compared to an unstructured mesh, wherein the software meshes the domain on its own using certain algorithms that have been defined by the software itself. So basically, structured mesh is was used earlier, like was really popular earlier, and also for like research applications. Many times, a structured mesh is preferred because it gives more flexibility with respect to the way that you want your mesh to look. That is, it gives you more flexibility when you want like certain areas to be more dense or certain areas to be more sparse as compared to unstructured. You can of course do that with unstructured mesh as well, but what happens over there is that you have less control over how the cells will be distributed over the domain. So although you might be able to define pretty well a lot of areas wherein you want more cells versus where you want less cells, etc. But structure just offers better control, better transparency as compared to unstructured. However, for big and complicated geometries, the unstructured mesh is preferred for complicated geometries because it is the unstructured mesh does not require any um, like does not require many rules and methodologies. So that gives us some flexibility with respect to how or what kind of domain we want to take. Since for structured, either if we take a complex domain and um, try to fit a structured mesh in it, it might require a lot of engineering effort. So both of they have their pros and cons, and it's up to you and up to your objective to decide which method you want to go with. So, once again, structured mesh requires knowledge about geometric transformations. So, basically, how we go about with structured mesh is that we look at certain rules and certain geometrical transformations to connect the physical plane with the numerical plane. So, one rule for structured mesh is that basically, uh, irrespective of how your domain looks, let's say your domain looks something like this. This is too complex. Let's just. This is what a domain is, whatever it might be, and you sort of want to fit a mesh which looks something like. Let's see if we just make that. So basically, what you're trying to do is that you're going to adhere to the geometry, adhere to the geometry that you have at hand, and try to create like cells out of it. So you're gonna do something like this. But your job doesn't finish over here. So basically, when we have this kind of a mesh, just entirely draw it. This needs to be transformed into a computational plane, which is an imaginary entity. Um, wherein what you need is that you need to have basically a square. I've drawn a rectangle over here, let's just make it into a square. It's not necessarily always a square, but basically you want something that okay, yeah. How many rows have we made? We've made 3 rows, it's fine. See, so we want a kind of a physical transformation which will correspond each of the point to the other. Like basically, if I have, let's mark the points with red. If I have this, these points should correspond to these points on the computational plane. So let's just define that. So you can see, like with the complex geometry that I have taken over here, how this might be a very complicated task to transform something that we have on the right to something that's on the left, because it requires an intimate knowledge of the equation of this particular curve, which is given in blue, and it requires you to have that knowledge at each and every point that you have over here. So that can be fairly tricky for complex geometries. Therefore, for complex geometries, typically it's a good idea to go with unstructured mesh, right? So for most cases, we just simply use some simple transformations to relate the physical and computational plane. Therefore, the kind of shapes that we can use with the structured mesh are kind of limited. Such as one popular example is when we look at an airfoil. Okay. Um, there. So the mesh around this can be represented by um, can be done using structured meshing. So there is a certain way to go about with it. So there are various, like structured meshing is actually a very sophisticated and a very intricate subject, and that does require a lot of knowledge about geometry, knowledge about how geometrical transformation happens, etc. And therefore it's a cumbersome subject, and there are various ways to go about with making a structured mesh, but all of them must be backed up with solid proof and solid transformations. So yeah, that's a requirement from our end as engineers. So I'm just going to finish drawing this. It's not a very good representation of what it might look like, but essentially you can understand that okay, these are my grid cells, and you would want something which looks again something like this on the right hand side. So basically, a requirement is to sort of map all of the different meshes that you might expect from different shapes onto a similar looking shape, so that we can go ahead and evaluate our values at each and every node point or each and every cell center fairly easily without having to make a lot of changes in our existing code. So that's the motivation behind using structured mesh. And nowadays, unstructured mesh is typically more popular, but structured mesh has proven its importance, and is many it's many times used for elementary studies because of their versatility with respect to size. Right. Okay. So this is the brief overview of the some ideas behind meshing. You can of course look at your lectures and have a deeper look at what is going on with these two types of meshes. Right. Okay, so we'll jump on to the questions now. So let's see what the first question is asking us. The first question is the grid size for the Cartesian grid in terms of control volumes is. We'll ask how many control volumes are here. So once again, let's recall what control volumes meant. So control volumes basically means the entire cell. It's asking us basically how many cells are there in this domain, right? So we can simply see how many rows and how many columns we get. So then there are 1, 2, 3, 4, 5, 5 rows, 2, 3, 4, 5, 6, 7, 8. So 8 into 5. So you can expect the answer to be D. That is, there are 8 into 5, that is 40 control volumes in this domain. So why is this question here? It's because we need to actively recall what we mean by control volume over here. That is, we mean the whole cell. We do not mean these lines. We do not mean the points. Okay, so we're not being asked how many points are there, because points will be different than the number of control volumes. So you can see over here, there are 6 points. Meanwhile, there are only 5 control volumes or 5 cells. So you need to remember and you need to be conscious of the fact that what you're being asked. Here, control volume refers to cell. It's the important takeaway from here. Right. So we'll move on to the next question. So the next question is about a uniform. Okay. Let's see what it tells us. A uniform Cartesian grid are shown below with the domain dimensions b equals to 2. Okay. H equals to 1. The value of delta x and delta y are. Okay, so we can see over here that it's a uniform type of a mesh. There's no biasing or there is no difference in the cell sizes anywhere. B is 2, right? And H is 1. So we ask what delta x and delta y are. So if we look at delta y, so we know that 1 has been divided into 1, 2, 3, 4, 5, 5 halves. So that means that your delta y is 0.2. Let's see what's happening with delta x. Let's see 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 divided by 8, that is 0.25 equals to delta x. So delta x is 0.25 and delta y is 0.2. So you can expect the answer to be D. Okay. So we'll move on to the next question. A stretched Cartesian mesh is shown below. The grid spacing along the height increases by a constant ratio of 1.1. Okay. And A and the first and smallest grid spacing is K equals to 1. Okay, so first let us appreciate what is given in this image. So here we have a biasing. That is, we have a stretched Cartesian mesh as written over here. As in, the cells that are closer to a certain boundary are smaller in size, and the cells away from that set boundary are larger in size. So we had discussed something similar earlier with respect to gradients. That is, when you have a gradient to capture. So typically when you're going to be looking at a boundary layer on a plate, for example, you're going to look something like this. Okay. So you can see that the gradients are really sharp near the boundary of interest. So if we were to not use this differential biasing, then we have two options with us. First, that you make all the cells small. Okay, everything small. But that might not always be a great idea, because what you're essentially doing is that even in areas where there's not too much variation or not too much information present, so you're still giving it a lot of attention. And what that does is that it increases your computational cost. So this is definitely not an option we would like to typically avail. The second option is to just ignore it, right? That's obviously also something you should not do. So therefore, this biasing allows us to put the required number of required size of cells where it's needed. So it's a need-based kind of operation, right? So over here, what have been we've been asked? We've been asked the total value of h. We've been asked how much is total h if the height increases by a constant ratio of 1.1, and this is equal to 1. Then if this is equal to 1, then the next cell will be equal to 1.1. Okay, because we have a constant ratio of constant ratio of 1.1. then that in turn would be 1.1 times of 1.1, that is 1.1 square. Similarly, we can see that this would be 1.1 cube and this would be 1.1. Let's write it down. So total H would be 1.1 plus 1.1 square plus 1. Sorry, 1 is also added over here, which is the smallest cell. Let's mark it. That's the smallest cell. 1.1 cube plus 1.14. You see, we have 5 cells over here and we have the length of all 5 cells. So computing that, let's see what that comes up to. It's 1 plus 1.1 plus 1.1 square plus 1.1 cube plus 1.124. That's coming out to be option A, that is 6.1051. Right, that's the right answer for this question. So we basically just looked at the ratio and saw how the cell sizes are related to the previous cell size, and we were able to easily evaluate the total length because we can see how many number of cells are present in this domain. I'm just going to write it down over here as well. Right. Then moving on. Okay. So we are asked, non-uniform grid spacing is required too. So what is the need for this type of a non-uniform grid spacing? So we just had a brief discussion about that in the previous question as well. So let's see what our options are. A, to reduce computational costs, of course. So we saw that how if you do not avail this option, that is if you don't have non-uniform grid spacing, then your other options to not to adequately capture the sharp gradients would be to have the same small cell size all over the domain, which would be fairly expensive. So that's something that we do not want to do. Therefore, reducing computational cost is one of the answers. Because throughout CFD, what we're trying to do is that we're trying to minimize the amount of useless work that the computer might have to do, since these algorithms can be fairly expensive and the domains that we typically deal with can be really large and can be really expensive if we do not avail the methods by which we can save our computation costs. So definitely to reduce computation cost is one. Second, let's see what the second option is. To capture sharp gradients accurately, that's also true. Like we saw in the previous question, if we did not have such a small cell in the first, like such a small size of the first cell, then we would be missing out on this sharp gradient. Like for example, I decide to put my first cell over here, and by that time, the velocity profile looks something like this. Then instead of capturing this gradient, which I need, I'm going to be capturing this, which isn't a very good approximation. It's not even close to what you need. Of course, once again, like with everything else with regards to CFD, we have to be careful about what we are going to be choosing to be important, because of course in physics there are a lot of phenomena that keep on happening, and you should be able to judge and accept that you're not going to be able to capture all the phenomena um, that are occurring in the said problem, and you should be able to judge that how much error that is inducing. So in this case, we judged that this kind of losing this gradient might not be a great idea, and therefore we go with this sort of non-uniform grid spacing. So to capture sharp gradients accurately is the second correct answer. So A, A is right. And post boundary conditions. Not really. This has nothing to do with the size of the cells because boundaries are something that exists over here beyond the cells, beyond the internal cells. So the size of the cells, of course, they do um, have a role to play when we are implementing the set boundaries, especially when we are looking at some Newman type boundaries. But on its own, this kind of non-uniform grid spacing does not do anything special for boundary condition implementation. So that's not the right answer. And B, none of the above is also not the right answer. So A and B, yeah, that makes sense in the current problem, right? So moving on, a three-dimensional grid can comprise of we are given like four types of cells. Quadrilateral, no, that cannot contain quadrilateral. Why? Because quadrilateral cells are planar, right? So they are 2D. So obviously that's not true. Hexahedral cells, yes, that is true because hexahedral cells look something like this. That is, they're prismatic in nature, and so this is a type of 3D cell. Then we have triangular cells. Obviously, these are also two-dimensional, and yeah, so that's not the right answer for this. And lastly, we have tetrahedral cells, which look something like this, right? So we have these four types of cells. So which of these are three-dimensional? It's B and D. That's a fairly simple question that we are able to evaluate. Okay, now for a three-dimensional grid, the cells can be either hexahedral or they can be tetrahedral. Okay, I'll just reorder shapes properly for your reference. Right. So we're looking at quadrilateral cells. This is A. I'm just drawing any quadrilateral. I'm not paying too much attention regarding what it looks like. Just a second. क्लास एक मिनट 5 मिनट कॉल करती हूँ right, so this is A, the representation of A. For hexahedral cells, you essentially may have something that looks like this. It's not a great drawing, but yeah, basically we're looking at something prismatic in nature. That's the crux of the matter. Then you have triangular, which you already know. It's like a triangle, which it is. Then finally we have the tetrahedral cells. So tetrahedral cells are also 3D. Audio is not clear. Is it clear now? Okay, okay, great, thanks. Right, so this is a tetrahedral type cell. So here we have A, B, C, and D. So clearly we can see that B and D are three-dimensional. Therefore, they are the right answer. Right. So moving on. Okay, here we have a nice and interesting question about transformation. So let's see what are we being asked. The non-dimensional lengths in the above figure are L equals to 1.6. So let's just keep on marking it in the figure wherever we can. Maybe use a better color. 1.6. Okay. H1 is 1. H2 is 0.6. Okay. and the transformation functions eta and nr. So now we need to know the transformation functions. Like I spoke about in the beginning of the session, basically what we need to do is that this is my physical plane and I need to find out what functions will transform each corresponding point. Like this should correspond to this should correspond to this should correspond to this, and this should correspond to this. So basically we want each and every corresponding point in the computational plane to be related by the same relation. So you can't switch the relation when you're dealing with transformation midway. So basically we are looking for a relation that will satisfy each of these points. So now we have a bunch of relations over here, and what we'll do is that instead of like really looking at each and every point like I have marked over here, we look at the four edge points because we have information about it, like short information about these 4 points. So let's write them. This is the xy plane, by the way. The physical plane is called the xy plane, and the computation plane is the sorry eta and eta plane. Okay, sorry, zeta and eta plane. Yeah, and right. So let's mark the points. So what is this? H1 is the whole of it is 1. So this means the x is 0 and the y is minus 0.5. Here the x is 1.6 and again, no, not minus 0.5. In this case it's minus 0.3. Over here it is 1.6 comma 0.3, and this point is corresponding to comma 0.5, right? So let's see if it's right. Yeah, looks right to me because this one will be divided into two halves, that is 0.5 and 0.5 above and below, and similarly for h2 will be divided into two halves by the x-axis. So now let's have a look at the zeta and eta plane. So what is this point corresponding to? Let's do it in another color so that we don't get confused. So this left bottom point, which is 0 comma minus 0.5 over here, is 0.0 here. This is 1 comma 0. This is 1 comma 1, and this is 0 comma 1. Okay, so now we need to see which relation is satisfying um, for all of our points. So let's look at first what the zeta should be. So zeta, let's go with point. I'm gonna mark the points also. I'm gonna give them a name. This is A, B, C, D, and correspondingly this is A, B, C, D. Right. So we look at point A. Looking at point A, so we have x is equals to 0, y equals to minus 0.5, and eta is equals to 0, and y is equals to also 0. So we don't get much useful information about eta from here. So we look at point B. So x in here is what? 1.6, y is minus 0.3, zeta is 1, and y is 0. So here we are able to see some relationship between x and zeta, which we are going to mark first. So then 1 is equals to x minus some factor a, so that is 1.6. So a is equals to 1.6. So basically zeta equals to x by 1.6. Right. Implies zeta is equals to x by 1.6. So we have narrowed it down to b and d. So that makes our job easier because as you can see that the expression for eta and y relation is going to be more complex because this contains like the parameters x and y both. Right. So once again, we look at point B because that seems like a nice point which is giving us some information. So, okay. So now we have eta. So eta over here is 0. Okay. So eta is 0. So 0 is equal to, we're looking at relation B first. For relation in option B, where is my eta? Eta is 0. Y over here is minus 0.3. Okay, understood. 1 minus 0.25 into x. What is my x? It's 1.6 plus 0.5. So evaluating this, what are we getting? I'm getting minus 0.3. I'm getting 1. I'm getting, uh, what am I getting from here? I'm getting 0.4, right? Is that right? So half of half, right? So 0.4 it is plus 0.5. So then I have over here minus 0.5 because this is going to be 0.6 plus 0.5, which is equal to 0. So this relation seems to be correct for at least point B. Just for confirmation, what we're going to do is that we're going to look at another point which is informative. That is, we look at point C. Confirming with confirming by looking, since we have two relations, so therefore just to see whether this is working for both the cases, like for all the cases. Confirming by looking at point C. Right. So I have 1 by 1, that is x equals to 1, y equal to 1. Then I have zeta. Zeta is equal to what for me? Oh, sorry. It's zeta and eta which are 1 because I was looking at the computational plane. Meanwhile, corresponding x and y are 1.6, comma 0.3. Okay, so once again, looking for a relation in option B, let's copy this. What's my relation in point option B? It says eta equals to y. Oh, sorry. Right. Thank you, thank you. It's supposed to be A, not B. Okay, the expressions for B in both A and B are same. Sorry, the expressions for eta in both A and B are same, so that helps me out. Okay, I just marked the wrong ones. Yeah, you're right, the value it's 1.1 by 1.6 as we have written over here. Mm-hmm. So now just evaluating for the same. So what is eta over here? 1. What is y over here? 0.3. What is x over here? It is again 1.6. So we have over here 1 minus 0.25 into 1.6. So yeah, we are getting 0.5 plus 0.5, which is 1. So we can now rest assured that our option A is right, not B. I'm sorry. Basically, what error I had made is that I had misread. I just didn't translate this option, this result to my options. So right. So we're not looking at option B. We're looking at option A. Right. Okay. So now we have our final question for today. So this is yet another transformation based question. So let's see what is written over here. So we're being told find the transformation function zeta and eta such that delta zeta is 0.1 and delta eta is 0.1 for L equals to 1.2. So we'll just keep on marking over here so that our life is not difficult. So this is L. So this entire thing is 1.2, right? And H1 is 0.8 and this is 1. H2 is 1.2. No, it's 1. It's not 1.2, it's 1. Right. L is 1.2 that we noted, H1 is 0.2 that we noted, and H2 is 1. Right. So once again, I'm going to just mark my important points, that these are four important points, that is the boundary points. Of course, all points are important, but these are the points that we have short information on. So why not use them to confirm our relations? So what is this? This is going to be 0, 0. This will be 1.2, 0. This will be 1.2, 1. And meanwhile, this will be 0, 0.8. So we have A, B, C, D. And here we have A, B, C, D as well. And we have been told that delta E and delta zeta and delta eta are both 0.1, which gives us the information that 0.1 plus 0.1 plus 0.1 plus 0.1. This is 0.4 and so is this. So both of these coordinates are max out at 0.4. So we'll just, this is simple to write, 0, 0, 0.4, 0.4, and then we have 0.4, 0. So next we want to see what is the relation between eta and zeta and x, because that's simple to find. So let's pick point C. So x, y, zeta, eta. It's a good practice to sort of write down the coordinates already so that we don't get confused. So here we can clearly see that eta is equals to x by 3, right? 0.4 equals to 1.2 by 3. So my x by 3 gives me, let's look carefully this time. X by 3 is an option B, that's a candidate option, and it's an option, yeah, option D. So these are the candidate options for the right answer. Now we need to cross check with respect to eta, right? For eta, right? So let's take the option B first. So we have 0.4 in here, we have 0.4 in here, we have y is 1, and we have 0.8, and we have x by 6, that is 1.2 by 6. So what we're going to have over here is 0.4 equals to 0.4 by 0.8 plus 0.2, which is 1. So 0.4 is 0.4. So this is a candidate option. This is most likely correct. But we'll just reconfirm for one. It's not really necessary. We know that since the relation is being satisfied, therefore this must be the right answer. But we'll check for one more point just for our own satisfaction. Let's take point B. Right. So point B is, actually no, let's not take point B because it doesn't have any information on eta. So we'll take point D. What is x and y in this case? X and y are 0 comma 0.8, and eta is 0, and zeta, sorry, yeah, zeta is 0 and eta is equal to 0.4. So now using that relation, so we have 0.4 is equals to 0.4 into y, in this case is 0.8, right? And we have 0.8 plus x by 6, that is 0 by 6, so that's 0. Then we have 0.4 equals to 0.4 into 0.8 by 0.8, which is once again 0.4, and therefore our answer B is confirmed. So you don't necessarily need to repeat these things twice. It's just to show that how when our transformation relation is correct, it's applying on all the points. This is a very important property of the transformation function, that each and every point should be transformed into the computational plane using the same function. That's a salient property for it to be called a transformation function. That's important. Right. So that's all I have for today. And yeah, this is also marks the end of the tutorial sessions that we've been having. So I would like to thank you for your patience and thank you for your attendance. And I hope the videos on YouTube help those of you who've not been attending out. And of course, you can reach out to me on my email when necessary. And if there's any problem which I cannot resolve, I'll forward it on to the professor as I've been doing. So all the best with your exams and your assignments, and yeah, keep in touch if you need something from me with respect to the more practical aspects of doing a PhD, etc. And yeah, thanks a lot. Okay, okay, see you. Bye.